Belgium, Frederic Moens, and he will introduce the SHIME and the Diamod system. Here we go.
Thank you, Andrea, for a nice introduction. So good afternoon, everybody. And indeed, today I will present you to the SHIME and Diamod technology platform. So first, a small introduction about the company. So ProDigest was founded in 2008. We have 40 employees working at ProDigest, and we are expanding. And we are actually a service provider, and we provide services towards external clients to accelerate, let's say, the R&D activities of these companies. And internationally, we have contracts with customers around Europe, USA, Asia, and Africa. So actually, we're active worldwide. So what is our expertise? That's the gastrointestinal tract, let's say. So what we actually do is we develop and we use unique laboratory setups that simulate the complete gastrointestinal tract. So the complete gastrointestinal tract, that means that we have both an artificial stomach, a small intestine, and a colon. And by using these models, we can answer different research questions. So we can focus on digestion, absorption, microbial fermentation in the colon, host microbiome interactions, probiotic survival, drug dissolution permeation, and targeted release dosage forms, among others. What is very important from, let's say, a preclinical view of point of view is that you always need to have a certain in vitro toolbox. So that means that we can generate tailor-made experimental setups, which are based on the compound characteristics, but also on the research question. And because of that flexibility, we can go to static models, let's say, where we can go for high throughput testing and separate parameter testing, because sometimes it's really important to really focus on one single parameter and then extrapolate it towards the broader scope. And from these static models, we can go to semi-dynamic models and then full dynamic models, which have a higher biorelevance, complexity, and will generate more information. So more parameters will influence each other. And in the full dynamic models, we have the SHIME model and the Diamod model, on which we will focus today. Always very important to take into account is when you want to build in vitro models which are in vivo predictive, then you need to simulate two things, let's say. On the one hand, you need to use biorelevant media, which is important, but you can use this biorelevant media in a beaker, let's say, in a static model. But when you combine this biorelevant media with biorelevant in vitro tools that really simulate, let's say, the complete dynamics and permeation of the gastrointestinal tract, then you get towards a clearer view and a better simulation of your system, being capable of actually simulating what is happening in vivo. And that's, let's say, the core expertise of ProDigest. So very briefly, I will introduce you to the SHIME technology platform, because I think numerous publications has come out since the development of that platform. So I will not go too much into detail here. So the in vitro gut simulator, the SHIME, so it's a simulator of the human intestinal microbial ecosystem. And it's a simulator that both simulates the physiology, but also the microbiology of the gastrointestinal tract. So when you look at the middle picture, let's say, this is a fully automated computer-controlled system, in vitro tool, that actually simulates what is happening in vivo. So in vivo, you have the segmentation, let's say. So first, food or whatever, an oral dosage form, enters the stomach, then it's emptied inside the duodenum, then it passes through the jejunum and the ileum, and then finally it enters the colon, and the colon is subdivided in the proximal, transversal, and distal colon. Each region, let's say, has a microenvironment of pH, of enzymes, of concentrations of different nutrients, but also a microbiota. So when we look at the SHIME system, let's say, and we go from the left to the right, you see that we have 6 reactors here. So 3 times a day, food enters the stomach, and then the stomach, in which the digestion starts, is emptied inside the duodenum, and the duodenum is then emptied in the ileum. And furthermore, the ileum is emptied into the colon, which is subdivided into the proximal, transversal, and distal colon. Very importantly, each of these compartments as its own physiology, but also its own microbiology. And next to only simulating the luminal microbiota, let's say, so the microbiota which is present in the lumen, we are also capable to simulate the microbiota which is attached to the mucosal surface that lines, let's say, the colonic site. And this we do by using mucus covered microcosms. So this is a fully dynamic system that we can use for long-term administration studies, and we can take samples from each of these different compartments and look where, let's say, a certain action is happening. So based on a research question, where is something degraded? Where is absorption happening? Where is a certain compound being dissolved or not? So that's one thing. So let's say the whole company was built around this SHIME model. So actually in the beginning, we were really focusing on the microbiota part, let's say. So we have the upper gastrointestinal part. So in the microbial part, we can look at drug-bug interactions, let's say, and targeted release dosage forms. So what we actually did was then we focused, let's say, on the upper gastrointestinal tract, and we actually wanted to improve this and to make it better based on the nice literature data that are now present in the community to really reflect, let's say, the upper gastrointestinal tract to be capable to get nice data about drug dissolution and permeation. And that's why the Diamod was created. So when we look at the Diamod technology platform, so the Diamod is the dynamic intestinal absorption model. So the keystones behind the development of the Diamod, let's say, is first of all, your dissolution should be good, simulated in an adequate way. So you need to have a biorelevant simulation of the dynamics of the gastrointestinal tract. So when you look at static in vitro models, you have, let's say, a gastric step in which you dissolve your compound or you just add your compound to the stomach phase, and then the stomach phase is poured out into the small intestinal phase. But this is not like it is happening in vivo. So in vivo, you have a lot of dynamics playing, and these dynamics have a big impact on the dissolution and the permeation of an oral substance. When you just look at, let's say, static models versus dynamic models, in a static model, your pH will be constant, or you have a constant low pH or a constant high pH. Yeah, of course, in vivo, in a fed state condition, you have a sigmoidal pH decrease. The volume in a static model in the gastric step, so when we look at the stomach in the upper part, is constant. In vivo, that's not the case because you have gastric emptying playing there. API concentration, static model, constant. In vivo, you have dilution due to gastric emptying and gastric secretions, and also the enzyme concentrations, because today we are talking about digestion models. Yeah, of course. Yeah, in a static model, you have constant high concentrations of enzymes, whereas in vivo, you have increasing enzyme concentrations due to the secretions. But also the enzyme activity is, let's say, differing in function of time, because the pH in your system is, let's say, changing in function of time. So that means that you have a dynamic substrate enzyme ratio. When we look at the small intestine, the same applies for the small intestine. In a static model, everything is constant. In vivo, it's not the case. You have a pH difference in between the duodenum and the duodenum. The API concentration is dynamic due to gastric emptying, duodenal emptying, and duodenal secretions. Your bile salt concentrations are dynamic in function of time. Also, your enzyme concentrations and the substrate enzyme ratio is dynamic in function of time. So, yeah, we were talking in the last talk of TNO about lipophilic compounds, so BCS2 compounds. So yeah, they have a very poor aqueous solubility. So there are a lot of enabling formulations now that try to overcome, let's say, this solubility limited bioavailability. So what you can do is increase the solubility of a compound, but that doesn't directly mean that you have an increased permeation, because there is something like the solubility permeability interplay. So when a drug enters your duodenum, it can be present as a molecular soluble drug, but it can also be entrapped in colloidal phases, like for instance with cyclodextrins, surfactants, and other formulations, or in a fed state conditions with food compounds and micelles. But of course, when we have a dissolution model, let's say that only simulates dissolution, you will both measure the apparent solubility and the molecular solubility. But it's only the free unbound drug that is capable to permeate across the small intestinal barrier. So there is a need for discrimination between apparent and molecular dissolved drug. So there is a need for an absorptive environment in a dynamic dissolution system. And that's why we came up with the Diamod. So what we wanted to do was we wanted to have a dynamic gastrointestinal tract to look at the dynamics of dissolution. But as is occurring in vivo, we wanted to interconnect, let's say, dissolution and absorption, and this in a physically interconnected way. So when you look at the Diamod, it's a two-compartmental system. This is the validated system. We have an extension towards the other regions of the gastrointestinal tract. And actually, in fact, you have the stomach at the start of an experiment. You will have a full dynamic system in which the stomach receives gastric secretions and then is emptied mono-exponentially or linearly, depending on the prandial state, inside a second vessel that comprises an inner vessel, which is surrounded by a semi-permeable membrane and a sink solution. So here the dissolution in the duodenum is happening, and your dissolution is physically interconnected with your permeation. So what you don't actually get is a dynamic dissolution model with interconnected online permeation. You can sample at each time point without disrupting the system. So you can really look at what is happening in the stomach, what is happening in the duodenum, what is happening in the blood, in the sink solution, let's say. We use in vivo relevant dissolution volumes and permeation surface to donor volume ratios. We are flexible in the pore size of the semi-permeable membrane. We have membranes that are compatible with excipients, biosalts, and enzymes. So the excipients will not cause any damage towards the permeation barrier. And of course, a system, an in vitro system, should be flexible. Everything is pH controllable, and we are flexible in all the different aspects, parameters of the system. Just to give you a small example of what the Diamod can do, we did an in vivo in vitro correlation study where we looked at the negative food effect on a weak basic compound in dinavir. So actually, when we look at the in vivo data, let's say, obtained by Carver in 1999, so in dinavir, indinavir is a weak basic drug with pKa's of 3.7 and 5.9. So it was shown that there is a negative food effect for indinavir. The hypothesis was that the negative food effect was due to the higher pH in the stomach and slower gastric emptying, because you have a weak base needs a very low pH in the stomach. So actually in this in vivo study, they performed fasted experiment and fed experiments with isocaloric meals. So a protein meal and a carbohydrate meal, let's say. And what you see is when they measured the pH of the stomach, you saw that when you have a protein meal, of course, the pH of the stomach is increased. And then you really see in the plasma concentrations that you have very low exposures of indinavir sulfate. When you have a fasted state condition, so the diamonds, then you have a very low pH in the stomach, and then you really see a very high exposure. However, when you have a carbohydrate meal, the pH of the stomach remains very low, and despite that, you still have a negative food effect. So there are a lot of different aspects that are playing here that generate that negative food effect. So what we actually did in the Diamod, we replicated that study completely the same, so with the same food, whatever. And what we actually performed was a fasted state condition. So if you look at the figure fasted, we performed a study, a fed state condition with a protein meal, so Ensure Plus, and we performed a fed state condition with a low pH in the stomach, so a carbohydrate meal. What we actually did was, okay, we collected samples in function of time, and we determined the area under the curve inside the duodenum of the solid concentration of the drug. And when you take the fasted state as 100%, then you see that the area under the curve of the solid concentration under an Ensure Plus condition decreases till 66%, which is actually not good, but not that bad, let's say. And when you have a low pH condition, so a low pH in the stomach under fed state conditions, you even see that the pH, that the area under the curve of the duodenum increases as compared to the fasted state condition. So not much to worry, let's say, about that negative food effect. This would have been the case when we would only look at dissolution, let's say. But in the Diamod, we have a dynamically interconnected dissolution and permeation. And when we then look at the absorbed fraction inside the Diamod, and we take the fasted state condition as 100% as the absorbed fraction, then you really see that ingestion of Ensure Plus decreases the permeated fraction with 73%. In vivo, it was 68%. And with a low pH fed meal, it decreases the permeated amount with 35%. In vivo, 45%. So actually the main point here is when we would only look at dynamic dissolution systems, they are only capable to generate kinetic data about the dissolution, and they will underestimate the food effect. But when you have dynamic dissolution systems with coupled online permeation like the Diamod, you generate kinetic data about dissolution of a drug, and you're capable to discriminate between solubilization and supersaturation, thereby more accurately predicting the kinetics of food effects on the final bioavailability. So to conclude, as a service provider in vitro models, I think it's very important that you always need to use an in vitro toolbox for preclinical testing to accelerate and de-risk product development. That you need to be capable to use static systems for high throughput and single parameter testing, that you need to have these dynamic systems for more complexity and more biorelevance. And the choice of that model is depending on your research question, the type of product that you are testing, and the stage of your product development. Furthermore, the colonic microbiota can have a huge impact on drug release, drug-bug interactions, and the digestion in general. So you have a region-specific microbiota, you have the ileal microbiota versus the proximal, transversal, and distal microbiota. You have a mucosal versus a luminal microbiota, and there should always be a translation of in vivo functionality towards the in vitro system. And the SHIME technology platform captures the complexity of the gastrointestinal tract and is capable of doing that. And the final absorption of a drug is, of course, depending on the dynamics of the gastrointestinal tract, dictating its dissolution and the solubility, permeability interplay. So you need to have an accurate simulation of the dynamics of the gastrointestinal tract to get a nice dissolution profile. And this should be interconnected physically with permeation to discriminate between apparent and molecular solubility. And the Diamod simulates this dynamically interconnected dissolution and permeation. And hereby, I want to thank you for your kind attention.